My name is Ulf Wiger, old Erlang veteran. I got in touch with Erlang back in '92. Started using it in '93, and I've been pretty much using it since. Joined Eternity some years ago, a couple of years ago, 2.5 years ago or something. I'm on the core software development team, and I and Dimitar over there are on the state channels team. So I thought I'd give you a little overview of what state channels are and what they are good for. So, short intro, and then outlining a few problems that state channels are meant to address. And then I'll give a short description of something called payment channels, which is sort of a simplified version of state channels. And then over to state channels, and then get specific about eternity's state channels. So, the more complex something is, the sillier you want to make the presentation. So, usually you in the blockchain world, usually when you discuss different use cases, you use the characters Alice and Bob. And we'll also bring in Mario here to introduce or to represent the wildness of the blockchain. And this will represent our eternity state channels image. So, a couple of other things we need to illustrate. We need the coins and transactions that we sign using cryptographic signatures that are then put into blocks, which eventually are stringed together into a blockchain. Okay, so a typical scenario would be that Alice wants some coffee. Bob provides coffee, Alice pays some coin and gets coffee in return. But now she wants to do this on the blockchain. Now, the blockchain is wild and trustless. And so Bob will produce something of value. Alice throws in a transaction onto the blockchain network. Somebody picks it up, puts it in a block. Now, Bob needs to note that the payment has been registered on the blockchain and eventually deliver coffee. Now, there are some problems here. Pretty slow. Either you have to wait until the transaction is safely on the chain. Usually you will wait for a number of blocks to pile up on top of it. Now in Bitcoin, for example, the block interval is 10 minutes. And so if you want, for example, 3 block confirmations to be sure that the payment is there, maybe you wouldn't for a cup of coffee, but then that's half an hour. So the coffee would be cold, Alice would be disappointed. So either you wait a number of transactions to be sure, or you do basically a zero trust exchange. You don't care if it's, or you just hope that it ends up on the blockchain. Now, the Eternity blockchain is a little bit faster, so you'd wait some seconds, but still. You also have to pay a fee for every transaction. The higher the fee, the greater the chance that your transaction is going to be prioritized by the block miner who collects transactions into a block. And this is up to every miner which transactions they want to include. So if you want to be cheap and have the lowest fee possible, chances are higher that you will have to wait until more lucrative transactions are packed into blocks. So essentially, this also means that there is no sort of micropayment, or everything is a micropayment, and we really want nano payments. Also, you could say that blockchains are about most expensive append-only file system ever devised. It is very compute intensive actually to verify all the blocks and everything. This translates into what we call gas cost, which is essentially how much CPU power you have to expend to verify transactions and contract calls and things like that. And of course, that translates into poor performance. And just to feel really bad, we often compare to Visa. If we want to be a really efficient payment instrument, yeah, Visa is a good example. Now, note that this is a logarithmic scale. So, Visa is up there with some 24,000 transactions per second, or at least it was that 2010 or something. PayPal has boasted some 450 transactions per second on some really busy day. Eternity, maximum throughput would be about 100 transactions per second. Ethereum, about 20. Bitcoin, 6 transactions per second. So it's pretty slow. Now, in order to get around this, for some years, there has been a development of something called payment channels. Ethereum is sort of getting payment channels now officially. There is a Bitcoin version called Lightning. And the idea is you go off-chain. You have your savings on the chain, and then you kind of move tokens off-chain, and then you could transact cheaply, and then occasionally checkpoint with the chain. So on the payment channel, you basically just have balances. Alice has some funds, Bob has some funds, and then it's still trustless. So if there are disputes, you have to go to the chain, and then you have to execute some protocol. So again, if Alice wants coffee, what you would do, and maybe this is your typical coffee card, where you you load some tokens or virtual money into your card, and then you go to I don't know which coffee houses have that. I have a Swedish version. You just basically, they scan your coffee card and they deduct your tokens, and then you get your coffee. So it's an on-chain transaction to lock some funds into the payment channel, and when you close it, it's another on-chain transaction. But once it's open, you can basically just transfer money very quickly and with no fee or very small fee. It depends slightly on how it's implemented. Now, trustless basically means that you always have to assume that the party you're transacting with is bad and is trying to cheat you. So, what you can do then is that you can basically close the channel and get out. And then there is a protocol there to make sure that the other party didn't close with, for example, an older state that was more beneficial to them. So you can fight it out on the chain. That's a little bit slow and expensive, but yeah, disputes usually are. But during the channel life cycle, you can transact quickly and cheaply. So in Eternity, we have no fees for off-chain transactions in the channel. So essentially, you do an on-chain transaction when you start it and when you close it. So it's basically 2 transactions on-chain, 2 fees, and then you can pretty much go on forever if you want to. and communication typically encrypted, but again, trustless. So now you would probably then limit how many tokens you put on in your channel. So if something goes really bad, that's the amount that you stand to lose potentially. Now, what are state channels then? Well, essentially they are payment channels, but with more complex states. So the state in a payment channel is just the token balance. On a state channel, you can have contracts. The contracts can have state. You can call a contract and have the channel state updated. Now, in a dispute situation, it could be that, say you're playing a game inside a channel, tic-tac-toe or possibly chess or something more complicated, and then you're approaching the end of the game and Bob realizes that you're about to win and refuses to move the final move. Then you can actually, as part of a dispute protocol, force the next move. So to avoid having one actor just decide to become non-responsive and not do the legal next step. So, what's special about eternity channels? Well, many of the state and payment channels that exist or that have been sort of moving towards the market for a number of years now, this is kind of tricky to get to work actually. They are implemented as services on top of Bitcoin or as contracts on top of Ethereum. So they're not really part of the chain. In Eternity, we decided to actually make them part of the chain. So the Eternity blockchain knows about state channels. So you have a channel object in the blockchain state tree, and the blockchain knows if the channel is active or if it's closing, and it knows about the dispute, time window, and things like that. And that for one thing, that means that when you're dealing with blockchain or state channels in Eternity, you know what the dispute protocol is because it's defined in the architecture. And even if there are different implementations on top, they all have to abide by the dispute protocol and the semantics that are designed into the chain. This also means that it can be done a lot cheaper, which means that we can run faster, we can support more channels, and more homogeneity. So, some of the on-chain transactions, obviously channel creation. You can also deposit and withdraw funds. So that's one way to, again, if you have, say, a coffee app, you could top it up when you want to keep using it. In order to be more safe, you can, for example, snapshot the state to the chain. So if you lose connectivity and say the other party wants to try to unilaterally close the channel, your snapshot would prevent them from closing with an earlier state. So that's sort of a way of securing that you have at least the progression until that point saved on the chain. And then the forced progress transaction. And then you, normally you would do a mutual close. This would be negotiated on the channel. And then you close cheaply and quickly with the latest state. Otherwise, you can do a unilateral close, a solo close, which basically, for example, if the other party is unresponsive or just basically went offline and you don't know where they are, you could actually close the transaction with your latest state, or presumably, and then there will be a dispute time window where the other party could come back online and say, no, here is an even fresher state. And that could be accepted if it was actually signed by both parties. Then the chain will know that this is a later state. And part of the dispute there is you would use a slash. That's what we call it then. If there is a solo close and you come in with a later state, that would be a slash transaction. And eventually you can do a settled transaction where you just say, okay, this is it. This is, we close on this. So, the updated life cycle is, you don't just have the open and close, you can also do updates, you can do snapshots and things like that during the life of the channel. So, the state of the channel, you have the participants. We have support only 2 participants, so it's 1-to-1 channels. For one thing, this actually makes the dispute protocol understandable. And just as with other disputes, legal disputes with more than one party, divorces with more than one spouse or more than 2 spouses are difficult. It's the same thing here. We have a round counter for every state transition. The round is up incremented, so that's where you know what is the later state. And then you have the state tree, where you have balances, you have contract states, you have the contract code, things like that. And the way that is implemented, it's called Patricia or Merkle-Patricia tree, where you can hash the levels up to a top level hash, which tells you exactly where, so you can cheaply compare 2 trees and know that this state tree is identical to the other without having to compare every object in the tree. So, typically then when we refer to a state, we have the round and then the top level state hash. So that's the hash of the entire tree. And then we have the signatures. So if it's cosigned state, then it's a stable, agreed upon state on the channel. So the protocol essentially looks like this. Bob would typically have a listen socket somewhere, and Alice proposes that you create a channel and sends some parameters to Bob, initial balance, for example, and some other things. She signs it. Now Bob agrees and cosigns the initial state, and then that goes to the chain. And typically you would wait a number of confirmations until you know it's securely on the chain, and then you can go on. Yeah, that's the chain. So that becomes the initial state on the chain. And then when you want to do an off-chain update, say that Alice wants to transfer 2 tokens to Bob. She creates an off-chain transaction with a round and then the new balances, and she signs it. Bob verifies the signature, verifies that the balances are actually correct, and accepts by co-signing and sending that back to Alice. So now both have an agreed upon new state. And so we prune the old state. We don't really need that anymore. And executing a contract would be the same thing. You send another type of transaction or another update operation, which is essentially the hash identity of the contract and some parameters. And then Alice executes that call and comes up with the resulting state. And then she signs that and she sends that to Bob with a new round and a signature. So, and Bob does the same thing, executes the call, compares the resulting state hash with what Alice had sent over, and if he gets the same result, he cosigns and sends that back. So then you have a new stable state that's cosigned by both. So, if Alice does something, tries to cheat, and sends a bad transaction, basically a faulty resulting state, whatever, now Bob could either send a message back saying, no, that doesn't work, and you could potentially continue, or Bob could decide to just bail out and solo close, for example. And then that would be with the latest cosigned state. So the way it works in Eternity is that we've implemented the channel state machine as a daemon inside the Eternity node. So then Alice would actually send an update request to its state channel daemon, which does the verification, sends a transaction back saying, please sign this. So Alice puts her signature on it because she doesn't really want to give the private key to the blockchain node that she's using, so she has to sign it. And then the signed transaction goes over to the other state machine instance that's serving Bob, and it sends that, verifies that transaction, sends it over to Bob and say, this looks good, will you sign it? Bob could of course check it himself, and he adds his signature, and that goes back all the way to Alice as information that now there is a new cosigned state. So what you'd have to do if you develop an app is that essentially you have the signing callbacks, but a lot of the tricky stuff is done by the Eternity node for you. So, the different closing states, you have the mutual close, which is where both parties agree, co-signed, happens instantly, and this is actually private because since both agree, you don't have to store any state on the blockchain, which is nice. So then what you did on the off-chain channel stays there. Now, but if there is a dispute, you actually have to store some state on the chain. Now, unfortunately, if there is you do a forced progress, you have to store the entire state on chain, which is we hope that we will be able to improve that. But the goal is to always expose as little state as possible so that you can maintain as much privacy as possible. Because anything that goes on the blockchain is public, essentially. Everybody else can read it, they can inspect any transaction that's on the chain. So, we've done some performance measurements. Some of these are a bit simple where we have basically both Alice and Bob are on the same node and you do all the signing on the same machine and everything. So typically, for example, the first one there, one channel just transferring tokens back and forth. On my laptop, I do over 100 transactions per second, one channel. Running 10 concurrent channels, again on the same laptop, it becomes CPU bound because eventually it's spending all its CPU doing the signing and verifying signatures mainly. But still, I get a total throughput of about 400 transactions per second. And the contract calls are a little bit more expensive because you have to do much more checking. But actually on the real chain, we've done about 25 transactions per second in one channel. A little bit more, I think Dimitar achieved 26 transactions per second in his test. We also have something called in-band messages. So if you have two apps, say you're implementing a game and you do a lot of rapid updates that don't necessarily, it doesn't constitute shared state. Actually, you perhaps you really don't want it to be shared state. It's just perhaps graphics updates or movement updates, whatever. So then you can just send whatever messages you want, and it's routed the same way, so you maintain order. There we can, I measured with 10 concurrent channels, just sending as many messages as I could back and forth on those in parallel. I clocked over 2,000 messages per second total on one node running on the machine. And so this becomes a way to scale up performance quite a lot, because essentially then you could run hundreds or possibly thousands of transactions per node in the network. So if you have lots of, say, thousands of nodes in the network, potentially there could be a ton of distributed or independent off-chain transactions happening on the system, which actually don't touch the chain, but they're sort of connected to the network. So for example, if you see articles about Ethereum possibly reaching 1 million transactions per second, this would be theoretically what their payment channel solution could possibly reach with some technology improvements and massive deployment or something. But this is the logic behind it. So at least in blockchain, relative to the blockchain speeds, this is really very fast, very lightweight, very cheap. And it gives better privacy than transactions that actually go onto the chain, although we feel that we can still improve the privacy. So, and it's cheaper, so it could potentially allow you to do nano payments, really, really cheap payments. And it's still trustless. You don't have to, since it's actually the signatures and the co-signing that is the guarantee that you agree. So you don't have to trust the other party, you don't have to trust the node, and you don't really have to trust the chain, at least not beyond the math of verifying the hashes and the signatures. Well, that was pretty much it. Do you have any questions? Yes?
What is the benefit of having this middleman in the state channel? Is it that he is an arbiter after the solo close for the last state, or?
So the main benefit is, we hope, is simplicity, relative simplicity. So one problem with different state channel projects so far is that they are so complicated that it's hard to figure out how to use them, and often the researchers working on certain projects have difficulty even building demo applications on their own state channel infrastructure.
But what it helps with is the dispute part, when the
No, the middleman, the cat in the middle. It's a pretty complex state machine. Actually, quite complex. Even by Erlang is great for state machine implementation, but this is a difficult state machine to implement, and so it's hard to get it right. So if, as an app developer, you have to implement the entire state machine, I don't think we would see that many apps. And also, state machine programming, especially in terms when you get into concurrency and different things that can happen, you have to potentially respond to events from the blockchain, events from the other party, and do all the state checking and everything. That would be a huge barrier to entry. And I think that's one reason why state channels still have been sort of remained promising for at least 3 years. It's like everyone loves the idea, everyone is waiting for them to sort of break through and become extremely useful. But in many cases, they end up being very, very difficult to use. So we're hoping that our model is easier because essentially, especially if you trust our implementation of the state machine, you send the requests and then you get a transaction back with as a signing request. Now you could maintain your own state tree and you could do all the checking if you want to. You would probably do some limited checking, but essentially then you would initiate something and you would sign it. You would probably do most of the checking on the requests that come over from the other side, but then at least you can trust that our state machine implementation has done a bunch of checking. Other things that we do, for example, is that we cache the state. So if you drop out, your app crashes, you run out of, your battery dies, you lose connectivity, then you can reconnect, and the node actually has a copy of the state. So you can just very quickly get back to where you were. And that state is then, when the channel closes, that state is garbage collected so that it doesn't stay there. So, yeah, there are things like that.
And does it work in a kind of transitive way as like a network? So if I have a channel with you and you have a channel with someone else, can I route something through you?
There is a technique designed for doing that. We don't support it yet. It's called hash locks, where you could have an intermediary where you do a certain type of, you essentially lock your funds, and then it can get sort of unlocked on the other side. So the intermediary can't really steal the funds. So you don't have to trust the intermediary, except they're supposed to forward it. So that is a way to sort of do multi-hop payments.
Are you planning to?
We are planning to support that, and it's mainly a thing that we want the contract language to support hash locks. Another thing that we're planning to support is what we call virtual channels. Essentially, then you could set up a state channel, for example, to a routing service or whatever, and then you could, say, query that routing service to find some other party that you want to set up a channel with, and then you negotiate the setup parameters with the intermediary, but then you start your own state machine and you do a direct connection to that other party. And the thing that would be different is that when you close, it doesn't go to the chain, it goes to the parent state channel. And the advantage of that would be that you could create channels extremely quickly, because once...
So there is a hierarchical structure on planet. There are some channels which goes...
channels within channels, so then you could create ad hoc channels extremely quickly. The dispute would be, essentially the intermediary becomes sort of an arbiter. So it has a state channel with the other party and a state channel with you, and updating the chain means that you co-sign the update of, say, the contract that represents a virtual chain. So then you don't have to wait for confirmations or whatever to, it's chain update, virtual chain update is pretty much instant. So then that opens up sort of a new dimension of ad hoc connectivity using state channels. So that's something that we will start working on very soon. So it's a high priority for us. Yes?
You talked about resolving disputes and how you might improve that, make it more efficient. So how would you do that? Could you use the snapshots, the intermediate snapshots, and say, I'm going to jump ahead to the most recent one?
The main thing that we want to improve is privacy. So the problem is, for example, that if you do a force progress of a contract, essentially a legal contract call, and you go to the chain because you're actually allowed to do it. This is one of the most complex things. You could write the contract, say if you're playing chess, you could have the contract written so that it actually, the state indicates whose turn it is. So if it's Bob's turn, then Alice couldn't force progress, couldn't actually force Bob to move, because the contract wouldn't allow her to do the next call. You could control it that way. But the big problem is not so much that the node where the channel is, because it had all the entire state, remember, so it could cheat and look at the state and verify that it's a valid call. But then that block, that transaction gets into a block and it gets sent to all other nodes, and they also have to be able to verify that it's a legal transaction. And then they need to have the state. So, but there are a bunch of weird cryptographic techniques that could possibly be used to, there is, for example, zero knowledge proof that I could not explain to you, but other people here might, that we might be able to use. There is one other optimization that we're planning, and that's what we would call a soft forced progress, where if you're in the channel and you're zipping along, and then suddenly Bob doesn't want to accept Alice's move or whatever, then what we want to do is to have Alice basically send a threat of a forced progress, sending that over and saying, this is the move I'm going to make, and you can co-sign it and we'll pretend this never happened, or it goes on the chain. And this is another area where having that middleman would help, because then that state machine knows it will automatically put it on the chain, so Alice doesn't have to do it. Other things that the middleman can help with is if it will monitor the chain. So if it detects a solo close, because you could do a solo close sort of out of band or sort of on the side in a sneaky way, but then our state machine would detect that, and if it has a later state, it will automatically post that. So, and then just report to the client that, hey, this happened now. So then you don't actually have to be there to respond, or you don't have to have the logic because it's already built in.